Hello everybody and welcome to another day of CS 202. Hope you all are doing pretty good today. Let me switch over to the iPad. There we go. Okay, had some issues with that earlier, but now it's working. So today we are going to continue talking about virtuals and a couple of other little things, and along this we are going to be talking about polymorphism and casting again. We're gonna revisit static cast, then dynamic cast, and then reinterpret cast, which I kind of introduced last class as well. Anyways, I hope you all had a good weekend and everything. So let me go ahead. And I think I'm going to start with casting because I want to show you an example of casting with Reinterpret cast that will help you complete assignment, whichever assignment is the one with the vault. 6, I think. Yeah, I think it's 6. The ordering is a little bit weird of the assignments because the overloading one being out of order. But yeah, 6. Okay, cool. All right, so for that, I'm actually going to switch over to this. There we go. Okay, cool. So I went ahead and created just a bunch of generic files here so that we can quickly jump into any of them. Just empty programs so that we can just start typing. So I wanted to kind of revisit the up and down casting, and I want to show you how dynamic cast can catch errors and that kind of thing. So let's start with that. So I have a class A, and class A has a public variable int x. Again, my generic typical example. And class B inherits from class A. In fact, you know, instead of calling it A, let's call it, why don't we call it something nice, like parent and child. Since that's kind of what they are, you know. Inherits from parent, and in this case, we're going to do it public as well. Okay, and this one will contain a int y, and both of them are going to contain a function called foo. That should be virtual, but for now we're not going to make it virtual so that we can remember that problem that we have if we don't, and then we'll go from there. Okay, so we'll say foo just prints out the name of the class that it's in. Okay, so right now, if we go ahead and say parent P, and if we say child C, if we say C dot foo, and we say P dot foo, we expect that each of these should print out parent and child, right? So let's go ahead and run that. Oh. Parent and child, okay? And so now let's go ahead and introduce pointers to this situation. So let's go ahead and make a parent pointer. We'll call it, I guess, pptr, and then a child pointer, which we're gonna call cptr. Okay, and now let's go ahead and make the parent pointer point to the child, and the child pointer point to the parent, and almost flip them back and forth. So for now, let's go ahead and start by making the child pointer, or actually the parent pointer. I don't like these names. We'll call it ptr1 and ptr, just ptr, because otherwise they look confusing to me. So ptr1 is going to get the address of the child, and now let's try to do ptr1 foo, And let's just do that one for now. So now we have this issue, right? This is the issue that we talked about last time. That PTR is 1 is pointing to what should be a child, right? And when we call foo, we should see child print out. But because of the binding that is happening at compile time, we're seeing instead the parent function called. So we said we can fix that by introducing the word virtual. Until now, this will actually associate to the right thing, as seen here. Now, if we try to, so in this case, we had a pointer, or we had an object. Well, technically, this is the address of this object, and that address is an address of type child, and we're casting it. Well, in this case, we're coercing it to an address of parent, you know, because we're not explicitly doing it. Now, we can implicitly do that by going ahead and putting the word cast in here. So the way we could do that is, well, let's go ahead and try out with a static cast and say cast this to a parent pointer. Like such. And we get the same thing, except this time, instead of letting the operating system, or not letting the compiler do it for us, we are explicitly saying cast this in a upcast, right? Yeah, we're upcasting. So before it was doing it, it's just we were sort of letting compiler do it, which would be coercion. Okay, and so here's the thing: if we try to do it the other way around, if we try to do it by doing PTR2 gets, let's try coercion, the address of actually, yeah. So let's try to make a parent into a child. Yeah. So that would be P. So get the address of P. If we try to do that without even calling the function, we get a error saying invalid conversion from parent pointer to child pointer. And it doesn't matter if you put that in as a manually, like that, because you're still going to get this error. And it makes sense because it's a bad thing what you're trying to do here. You're trying to cast an object that is for sure a parent into a pointer that's child. And if you were able to get away with that, then it would be perfectly legal for you to call PTR2 foo. And that should call the child foo. However, the child foo could, in theory, access variable y. You know, it could even see out y after the child word. But there is no such variable in parent. But by having this become having a pointer of an object of a parent being pointed by the child, that means that you can call any of the functions or variables from the child, which don't even exist in that object. So in this case, we are essentially downcasting, and that's really bad. And just to make sure I don't get the name slipped, let me just look at my own little refresher on that. So upcasting is child to parent, and downcasting is parent to child, okay? And in this case, we are trying to take a parent object and cast it into a child. So yeah, okay. So cool. So this is bad, right? And this is typically not what you would end up doing. More than likely, where you end up with a situation where you would be doing this casting back and forth is if you had code that looked more like this. So if we have a pointer of each of those, and then we have a situation where, let's go ahead and, first of all, let's switch these to be dynamic. So parent P gets new P. Or actually, before we do that, I kind of want to try something first. Let's just put an if statement. if cn, so let's make it int x here, cn x, and then if x is not equal to, or simply just if x, so if not equal to 0, then it'll be the same thing. Then we will run this line of code. Otherwise, we will run this line of code. And then let's go ahead and try to do that. In this case, oh, well, hold on. Then I have to, what am I trying to do here? Let me think for a second. What am I doing? Okay, sorry. Long day. Let's try to make this dynamic. The point that what I'm trying to show you is that I'm gonna fool the compiler into not knowing what is really in what. Okay? And that's not because I'm trying to be sneaky, but because this actually could happen. And this is when dynamic cast will come to the rescue, essentially. That's kind of the end game of what I'm trying to do here. So if this line of code runs, then we will try to cast PTR I'm trying to see what how could I do this? I mean, here. What about just this? Let's see if this will work. Like that. Okay. I just want to test if this will work. Okay. Now I kind of got what I was trying to, what I think I can probably do. I can put the if statement here, so I can say if x we can go ahead. What we can do is we can make a pointer child c before it, and then in here we can say that child c is going to have a new c. No, parent. Let's do it with a parent. Well, we can do it with both, actually. So child c gets new c, and then also parent p. Like that is going to get p gets new parent and new child. That's what I'm trying to say here. Okay, and then otherwise, then p gets new c, new child, and c gets new parent. Let's try that. And if I can't remember what I'm trying to do, I can just we did it last time, so we can just copy from there. Okay, so c gets new parent is the one that is not liking here. Yeah. I'm trying to flip them around, basically. Or cause a situation where they would flip. That would be a problem. Okay, so this compiles now, but did I really achieve what I wanted to do? Let me see what I did last time. Why am I missing a 7 on my list of counts? That's weird. Okay, so PTR was a parent pointer, and we made it point to here so you can see. PTR was a parent pointer, and we made a point either to a parent or to a child. Okay. So maybe I'm trying to do something that I really shouldn't be doing here with the child. Yeah, okay. So forget all of this stuff. And let's just simplify the example into something way easier. So we have one object right now that we're going to call parent. And that pointer, or sorry, child, we're going to use a child. And that's going to contain a child actually in it. Okay, so we're going to call that C. And now you saw that we can cast this into a parent. So I'm going to have a parent called PTR. And I can go ahead and do something like this. Okay? This is casting a child into a parent. Now I can bring it back into a child pointer. So if I make another child pointer called C2, and I go ahead and bring it back like this, I can say C2 gets PTR. And this is casting it back into it. Okay? Yes. That's what I'm trying to do. Now I just gotta get rid of all of these things. Cannot convert. Oh, I forgot an asterisk. Why am I getting this? Where is this word child coming from? What am I doing? This should be C here. Yeah, I don't know. Okay, let me try actually cutting ahead and putting this in here. Well, and technically that would be coercion when you're doing that. Okay, so shake my head. What I'm trying to do is show you a reason when dynamic casting would be useful, but well, I can't even get it to compile. But by adding it, you can see that it compiles. Okay, so let's just cut to the chase of what I'm trying to show you. Instead of me, I'm really trying to show you a situation where this is a problem, but the compiler is not even letting me compile a situation like that. It's just like, nope, this is bad, and I know it's bad, but like I want it to let me show you that it's bad, but it's not. So instead, we'll just cut to the solution, which is using dynamic cast, which will then let me do it. So okay, so I could swear that there's a way I can get away with this, but the compiler is really not letting me. So let me tell you what I've been trying to do for the past like 10 minutes here. So I have a pointer of a child, okay, and it's pointing to a child object. Okay, so if I here, I know what I can do here. Let me yeah, perfect. Okay, so I got an object here that is actually a child. Okay, so this is it's a child, okay? And I also have a pointer called C, which is a pointer of child type, okay? And right now, it is pointing to a child. So that's step one, okay? That's gonna be line 22 of the code. All right? And tell me please if I lose you, all right? This is line 1. Or 22, I mean, okay? Line 23 is going to say to create a pointer of parent type, okay? And that pointer is called PTR. And right now it is who knows pointing to what, because it's not initialized. So it's like, we'll put a question mark because it's like, who knows where that's pointing to. All right, cool. Line 24 is basically setting that pointer to no longer just point to who knows what, but it is actually copying the value of whatever C is pointing to. And C, it happens to be pointing to C100, which is where this guy lives. So now this will also have C100 here. Let me scoot that over just a little bit here so you can see it, which means that it is now pointing to this. So we have two pointers. One is of child pointer type and the other one is of parent pointer type, and they're both pointing to one object called child. But here's the situation now. This is the risky part, okay? We know, because we coded this, that even though this is a parent pointer, it is really containing a child object. Now the compiler has no problems with you casting or coercing a parent into a child. So when we did the PTR get C, there was coercion happening there, which was a child pointer, became a parent pointer. So in the hierarchy of things, we basically made it something that was a child into a parent. That makes us technically lose access to things, because whereas with a, in the example we have an X and a Y, right? So whereas with the parent pointer, or the child pointer, in both of those I can access X like this without problem. Only within a child pointer can I access Y. I cannot do that from an X pointer. The reason being, from a parent pointer. The reason being is because it thinks it's a parent, and it's like a parent doesn't have a Y. It only has an X in it, right? And so we lose access to that. And that's okay, because that's kind of what we're trying to do. But the other way around is the really, really, really bad part that is not even letting me compile. And that is, if I have an object that is really a parent, but I cast it into a child pointer, which would basically say, if I go ahead in here and I make an object right now, and this object is of a parent right here, and it's somewhere in memory, and then I make a child point to it, something like that, that is going to be very problematic, because if I get away with that, I can go ahead and call any of the child's functions or variables, and the code will compile. Okay? However, normally, as you saw, the code doesn't compile if I try to do such casting. But technically, I'm doing the same thing here in this line of code, because at this point, PTR is a parent pointer, which might as well be pointing to an actual parent. And now I am casting it into a child pointer. But as you saw there, it wasn't compiling by putting the word static cast in front of it, or just not putting anything into it. It was not compiling at all. It was like, nope, this is a bad thing to do, because you can't cast basically invalid conversion from a parent to a child. It's not, and now you could get around with the permissive stuff, but again, that's not really good in the first place. However, the moment that I added this magic word of dynamic cast, the compiler shut up and didn't complain anymore finally. However, it's not a good thing actually that it shut up. In this case, it's good for me because I was getting frustrated, but it's not good. However, what is happening, and this is what I was trying to say at the end of the last class, is dynamic casting is a little bit more relaxed with these pointer stuff at compile time. However, it left that checking at runtime. So what's going to happen is when I run the program now, if this is okay to do, then the cast will succeed, and then it'll copy the same address, just change the pointer type. So it'll copy, so line 27 is going to basically take our child 2 pointer. So if we have basically another one of these squares. I'll just draw it again. So we have another pointer here called pointer of child, which is C2, which right now is pointing to, again, who knows what, because it's not initialized. And we are going to, let me move this for a minute over here. We are going to make that point not directly to child technically. Well, it will point to child. That'll be the end game. But the way we're doing it is we're copying the data from the parent pointer, okay? And so it's basically saying, I'm gonna wait until runtime to figure out if this is good or not. If it's good, you'll get the address into C2. If it's bad, dynamic casting will give you a null or a 0 or same thing in that address. I think you said this happens pretty much only when you poorly design your program. No. I mean, don't get me wrong. I'm going to show you today a very good reason why you'd want to do this, which is what I kind of mentioned last time about making an array that points to different objects, which is kind of cool and has usages to it. But in other scenarios, aside from that sort of situation, then yes, it really shouldn't happen because it means you screwed up in the casting. But so let me just show you the scenario where I have a actual parent object that we're going to call P, and that parent object contains an actual parent in it. And so the really, really bad thing would be to make this child 2, so instead of this one, to basically point to an object that's a child. So something like that. That's really bad because what am I gonna P? Let's go back. P like that and that. So this is really bad because now we are making a child pointer point to a parent object. You know, basically copying the pointer from a parent pointer to a child pointer, but it's really pointing to a parent. That's really bad because if I do P dot what's in child is not Y, or not, sorry, C2Y, you know, that's bad because there is no such variable in P, okay? Now, I'll test that in a second, but here, this is gonna again give me that error. It's gonna complain about invalid conversion. However, if I add the dynamic cast in front of it, it's not gonna complain anymore, which again, is kind of what I was trying to get to, but I was really hoping to get a way of compiling it without that error, and then I would show you how really bad it would be to call this, because then the program would crash. But can't think of a way of doing that, so it's okay. Let's cast this into a child pointer of this guy. Okay, and now it compiles and it runs. However, the bad thing here is if I do this, I am going to crash. Well, I didn't quite crash, but it's accessing something it shouldn't, because you guys know that it's impossible for C2Y to exist because there is no Y here because it's pointing to a parent, and a parent has an X and a foo. There is no such thing as a Y. So if I go ahead and actually just see out the address of, actually I don't need parentheses, order of operations makes it okay. Then this is an address that is not part of my object. It's just somewhere outside of memory of my linting. See? That's not even like a good looking address at all. That's kind of scary looking too. And if I try to write something to it, I think I should crash. There we go, we crashed. See? Fine. Yeah, thank you. The one time I want something to crash, it doesn't crash, right? Why doesn't that happen when we don't want programs to crash? So, you might have been able to do it with C++ 11. Yeah, that's true. I never thought about that. Yeah, oh well. It's okay. But anyway, you know, so you're like, why would I want to use dynamic cast? It's only going to make my programs risky again, and show you the whole reason why this ever want to do this. But it's important that you guys understand why this code is, what this code is actually doing at all, and why it's crashing and all these things. So it's, I know it's basically 8 lines of code, but they're important because it's important to understand why this is bad, but at the same time why it's necessary to do some things that we're going to do. So let's go over it one last time. Okay, so we got two objects. This whole thing is just two objects, right? There's a child object in C and there's a parent object in P. Those are the only objects. Everything else is pointers. We got three pointers. We got a parent pointer, actually 2 pointers. We got a parent pointer and a child pointer called PTR and C2. Okay? So in this line of code, we are taking C, which is a child, and it's just, you know, C itself is a child pointer that points to an object of child, and we are copying it into a parent pointer. And so that is doing the idea of making this arrow here happen. This arrow is a result of that line of code. That is considered taking a child pointer, or taking a child pointer and making it point by a parent pointer is upcasting, right? So we are making something point to a parent. Yeah, so that would be upcasting. Really get them confused. That's why I put them right with that. Then the bad line or the risky line is going back down. So taking something that is a parent pointer and copying it into a child pointer. In that case, we are downcasting because we are making, we're telling the compiler to treat this parent object as a child object, which gives us access to all of the functions and variables that a child object would have. We only can achieve this, the compiler doesn't let us get away with this if we use dynamic cast, or when we talk about reinterpret cast, yeah, but dynamic cast. You can't do that with static cast or with coercion, which is not putting any casting at all. As you saw, we get a thing that says invalid conversion from that. So the compiler is trying to help us out here by not letting us do something that we may potentially regret. Because here's the situation. You only really ever want to do this casting down from potentially something of a parent to a child if you know ahead of time that it really was a child in the first place. If it was, you know, there's a reason why you may want to keep this as a parent temporarily and then bring it back to child. That's a perfectly valid usage of this. You know, it's like, yeah, it's not really a parent, it's a child, so it's okay. That's fine. What is not fine is what I'm doing here, what is really I'm casting a parent to a child. Because then, as you see, when I try to access the variables, bad things happen. Now, there's a very specific reason why this was address 0C. And it's not something that would happen at one time. It will always be that address. And that is because the checking that is done at runtime is to verify that even that the casting of a parent to a child is okay. And how does it verify that? It sees what really is being held in P. It knows P is a parent pointer, but there's a small chance that it's actually being held by a child because we did the whole switching here. How would that be the scenario? That scenario, that would be if I went ahead and said P, and I know memory leaks and all, is actually C2 or C. Okay? In that scenario, when I'm doing my downcasting here, I'm downcasting parent to child, but the reality of things is that P isn't a parent. P is really a child because I had one here. So I sort of up and downcast it. In this scenario, if I run this code, it works just fine. No segmentation fault. And yet again, if I try to get rid of the dynamic cast, it wouldn't have compiled in the first place. It would have told me that invalid conversion situation as you see before. You kind of see it here. It's that error, so yeah. Okay. So does that make sense? Are we all on the same page? How do we feel about that? Again, this dynamic casting allows us to do things that we normally wouldn't be able to do because of the checking of the error, and it defers to it at runtime. And so here's what happens. When that casting happens and it sees at runtime that it's still a bad idea because we have a parent here and we're making it into a child, if it actually sees that that's the scenario, as is the case as I have the code now, if I take this line of code out, then I am really casting a parent into a child. Whereas in a crashes, Whereas in the other scenario, I am technically, even though I say I'm casting a parent to a child, it's not really a parent, it's a child. So I'm just casting child to child, so it's okay. So what's happening is at runtime, it's actually looking at what the object really is. No matter what the pointer type is, it's looking at what the object really is. And if it's okay to do the casting, it gives me the address back, the correct address. However, if the casting is bad, it's going to give me a 0. And that's why I am getting this address that starts with 0 here, because, or that's really small, because really when you're accessing variables such as the variable here y or the variable here x, it's really just a shift of the location of the object. This is actually at location 0 probably, and then this is at location 4, or as we saw here, the reality is, because of the function, this is at location c, which is 12. So it's probably like 4, 8, and then 12. So that's why that's at 12. Okay, so it's kind of tricky stuff. So let me show you an actual good scenario of when this will be becoming useful, that is not just intentionally trying to do bad things. Okay, and then from there we'll kind of go into the discussion about the assignments that I want to show as well. So if you still feel shaky on this, then it will hopefully be reinforced in a second. Let's talk about making that animal farm that we wanted to make. Okay, so we're gonna have a class animal, and we're not trying to make some super advanced thing here. So we are just going to have each animal have a name. And in addition to that, we're gonna need a way of identifying. Well, we can use the name. We can also use the name for that. So yeah, we'll just make the name. And also a function. Yeah, why not? Speak. The animal can speak. However, because of the concept that I talked about earlier, even though this will be an animal farm made up of a bunch of animals, and we'll start out by making 3 animals. We'll make a dog, a pig, and a cow. So this will be dog inherits publicly from animal. We will probably want okay, we'll add something later, but yeah. Trying to keep this as simple as possible. So here we have a dog, and now we're gonna make 2 more animals. Why not? So again, this could be a cow, which will make a moo, and then we will make a chicken. Well, how does a chicken make? Like, coo coo coo? I don't know. Okay, so Bagok? What? That is not the sound a chicken makes. Let's just pick a pig. That's easier. Boink. I don't think there's an internationally recognized sound for a chicken. Buck buck. That does not sound like a chicken. That sounds like a special dog or something. Like a dog that's like can't bark properly. So it's like bark 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 bark. So oink. Let's just go with the pig. All right. And yeah. So first thing is first. We don't want to. We don't want there to be a thing as an animal, because that's weird. Like. There is no such thing as an animal. There's a dog, there's a cow, there's a pig, but there isn't something that just identifies as generically as an animal. It doesn't apply. So we wanna make this an abstract class. We figured out how to do that a couple of days ago. We just make this variable equal to 0. And now there can never be an animal. Okay? It's just a generic coverall. And then we define these to stop the abstractness of the class per se, by writing the function. Okay, cool. So great. Let's just make sure that this all compiles nice and fine. Okay. So what I want to do is I want to create an array where I can keep my animals nice and happy. And so let's go ahead and make a two-dimensional array. Actually, let's do one dimension. Why do 2 dimensions? Necessarily complicated. So we're going to call it the animal farm. And it's just going to be made up of a single pointer, because we'll do it dynamically, because why not? We'll make this dynamic, so we'll call this an animal pointer called animal farm, okay? And that's just going to be actually a double pointer, because it's going to be an array of pointers. So new animal pointer, and our animal farm has a capacity of 10 animals. Okay, so what I made here is a array of animal pointers. They're not pointing to anything in specific. In fact, if you want to feel good about yourself, we can go ahead and initialize them to 0. I'm not going to make actually to be able to make this code flexible in case we want to change it later. We're going to use a variable called size, which is or capacity, I guess. That sounds better. Okay. So for int I is equal to 0, I is less than capacity, I plus plus. And so here we got a little loop. And for now, we are going to set each of those variables, pointer variables, to be null. Okay? So let's make sure everything is good. All right. So we got our farm, it's empty, ready to go. Let's start filling it up with stuff. So let's say that in spot 0 of the farm, I like to store a dog in there. So I can go ahead and say animal farm gets new dog. This, think about what this is doing. Because I am getting an issue here that's saying animal farm, hold on. Spot 0, there we go. This is saying make a dog, which is of a child of animal, and then there is casting going on here. There's upcasting going on, right? Because this here is a child class or a derived class, and this is the base class. So there is casting going on, but we're letting the compiler do it implicitly, right? That's coercion. So if we want to be, safe about what's happening here, or explicit about what's happening here, we couldn't technically write static cast animal pointer new dog, and we wouldn't see anything happen. But now we're being explicit. We could even go a mile further and use dynamic cast just to make sure that no bad things are happening, because then it'll do some runtime checks. Okay, so let's go ahead and make a couple of more animals. Maybe we'll put a loop in here, and maybe animals 1 through capacity, if the number is even. If I mod 2 here, let me get rid of this thing. Now I don't think we need this anymore in the drawing. Yeah, so if I mod 2 is equal to 0, then that's going to be a cow. So animal farm sub-I gets new cow. And again, there is a upcasting that's going to happen. So because I want to be a good safe programmer, I am going to go ahead and put this. Yeah. Thanks for catching that. And then otherwise, animal farm survive is going to get dynamic cast animal pointer new In the case that it's an odd number, it's going to get a pig. Okay? So, you know, they always told you don't try this at home kind of thing, but we're trying this at home in the sense of like we're keeping a array that contains multiple types in it. Even though an array, you know, they say it's homogeneous, everything should be the same type. We're keeping different things. Now we got a little crash here. Not to worry. Let's find out why we crashed by using GDB. Yeah, let's use GDB. Dab. So how do we use GDB? Okay, so we got G++ CASP. We're going to put the -G, which is going to add line numbers to each of the it's gonna basically associate your C++ code to the assembly code, so that when you run GDB, it tells you where it crashed. So the way you run GDB is you type in GDB, and you get this little nice little introduction to the GB. At which point you can just go ahead and type in the actually the shortcut to running this. By the way, to quit the GDB, type in quit. If you try using GDB and Control-C, it's just gonna laugh at you. So the easiest way to run GDB is to type GDB and then put in a.out, which is the name of the executable. Then you can just type in R for run. If you had command line arguments, you would type them here. So like, I don't know, 136 is also command line arguments. But anyway, you run this. Then if you do sec fault, not only is it going to tell you the line number, but it's also going to tell you what's in that line. So this is telling me that it is crashing in line 28 of my cast.cpp file, and that line happens to have the line animal farm 0 gets dynamic cast animal pointer new dog. That is useful because now I know where to start looking instead of just like praying, you know, of where this is happening. Furthermore, if you have actual real code that has like functions and everything, you can actually see the order of how you reach that function by typing the command backtrace. In this case, there's not much because it's just main where I crash. But suppose that main called function foo, which calls function bar, which called function potato, and your crash happened in potato. But like you call potato like 20 different times in your code. You know, sometimes you call it directly, sometimes you call it only via bar, sometimes you call it via foo, which calls bar, which calls potato. This will tell you the chain of how you got there, which is very useful to see like in which instant did potato crash, with what arguments and things like that. It'll also tell you the parameters up here if it was the case. So yes, this is very, very useful. No, print statements are for the weak. But yeah. So anyways, so we crashed at line 28, animal farm 0. Why did we crash at that line? This is a animal farm, new animal pointer capacity. Thinking here, this is a list of pointers, and we're copying the address of the pointer. No, it doesn't have to be, or at least it shouldn't be. This wouldn't have compiled otherwise, and we need a pointer here because this is an array of pointers. We don't want this to be objects. Oh, yeah. That's why it's crashing. Good catch. Yeah, we're trying to initialize the pointers, not the whole thing to null. So yes, that would explain why it crashed. So as you can see, the GDB is not the all be all, because I mean it does tell us where we crashed, but doesn't necessarily tell us exactly where the error happened. Whereas the error was actually right above it in this case, but it could have been anywhere else in the code. But at least it told me that the problem was involving animal farm array, you know. Anyways, if you want to quit this, you can do this, or type in quit properly. If it asks you if you want to kill it, then just say yes. Let the past die. It's the only way. So yeah, okay. So anyways, if we run this again, it doesn't crash this time, so that's good. So anyways, I do have a video on GDB. There's a lot more you can do in GDB. You can actually watch code run by line. You can put in breakpoints as well. It's been a while if I haven't done that, but maybe I can remember. I think it's break, and then you put a number here, so like maybe break 20. Yeah, so what that sets up a breakpoint at line 24 in your code, which should be this line up here. So then if I type in run, it'll actually stop at the breakpoint. And then if I want to go one line down, I think it's S. Yeah, so S will take me one line at a time. As you can see here, it's going through the loop. There's a way to exit, to get step out. I don't remember that one. But anyways, now I got past that. So now it's running that line of code at line 28. Then now it's running, and oh, that's cool. So that line of code is technically a new call, right? So it's calling probably the constructor and whatnot. So it's going into class dog, as we can see there. If I type in backtrace right there, you can see now that I am inside of this dog, specifically this object of dog, which was called by line 28. So there you can see the call stack actually working. Anyways, I'm going to continue stepping. The dog class called the parent class to create that. Because remember, when you call a derived class, it first runs the constructor of the parent class and then runs the constructor of the child class. So if I type backtrace now, you can see my call stack is growing, right? Because now I'm currently an animal, which was called by dog, which was called by main. So if there was a crash in the constructor in animal, I'd actually would see this as my call stack. So that's pretty cool. How do you run a program on GDB? Type GDB space name of the executable, which is a.out typically, unless you change the name. And then you type in GDB space R for running it. But before you run it, in the case of this, I put up a breakpoint by putting B and a number, which represents the line number in my C++ code where I want the code to pause. And then from there, I can watch it line by line so I can monitor the code and see if things go the wrong way. So let's just continue stepping here. Now I'm in lines 29 and 30. And here I can see that this time it is making a pig. Then and we can see the constructor is being called and whatnot. Then the next time it's making a cow and back and forth. And I don't remember the other commands because I don't usually use them, but there's a command to run till the end of the program. It's a letter. We can type in random letters and see what happens. Let's try A, F, nope, G, H. I don't know. Anyways, let's just quit it. Usually, you would remember these commands if you use this regularly, but there are other debuggers that you can use that are doing this. But S will be to step line by line. There's also step in. Well, actually, I believe it's step into every single time. There's also step out, and there's also step over. Again, in the video, I think I have those saved. And if not, I have a link to them. But the biggest thing of GDB is you can see that I was able to just run the program and see where things take fault, which is a blessing. So yeah. Anyways, GDB, use it or suffer, pretty much. Not that I want you to make you suffer, but I'm saying you probably will suffer if you just stare at code hoping to find where something is crashing. For like the binary illumination, where like light points at the line of code that's bad. That's not gonna happen. And if it does, then you probably would want that to be something other than just to fix code. So, you know, point me to like the lottery ticket number. Don't point me to how to solve this code. I can solve that, you know, given enough time. So anyways, now we got ourselves a bunch of cows and pigs and a dog. One dog, okay? So now, here's the cool thing. I got an array of basically different animals in this farm. And they're all being kept within one array, even though arrays should be only one type. The issue comes in, how do I identify what's what? And how do I confirm that things were stored correctly? So let's go ahead and run through a little for loop where we make each of the animals speak so they can identify who they are. Request for member speak, which is a pointer to, oh, yeah. If you always get that error, if you ever get that error, you know, read it and look at the bottom part. Maybe you meant to use the arrow operator. And the answer is, yes, I did. Thank you for reminding me. Oh, it might help to put an line after each of these, or just a line feed. Doesn't have to be an line. Otherwise, we got basically the animals' chaos, like mad chaos going on. You're like, shut up, animals. These are cage-free animals, by the way. So okay. So we got Wolf, the dog. Then we got Oink Moo, Oink Moo, Oink Moo, Oink Moo. So we got 1, 2, 3, 4, 5 pigs and 4 cows. So yeah, interesting. I think we should have had more cows, but why not? Okay. So it works, right? Now here's the thing. The dog has a special ability. Okay. And that special ability is going to be, or actually let's make the cow have special ability. And that's that you can milk the cow. If you want to get that fresh milk from the cow. So it's going to be called milking, I guess. So it's going to be a function called milk. And it's going to be like, milk has been created. I don't know. Okay? That's just a function what it will do. So now, we want to milk only the cows. We don't want to milk the dog, and we don't want to milk the pigs, okay? I think in theory you could if they were lactating, but I don't think people like to drink dog milk or chick or pig milk. So yeah, exactly. So they might be milkable, but it's not, it's not okay in society, I suppose, unless the dog had puppies and the puppies couldn't get the milk out or something, I suppose. So yeah. Okay. Anyways, moving on from that dark place. Let's go ahead and figure out. Here's the thing: we can't do this. It's not even gonna let us do this. If we try to do animal farm, so if I milk, this code will not even compile. It's gonna be like there is no such function in animal farm, because here's the thing: animal farm is a pointer of the parent, which is animal, and no such function exists in animal. So this will say no memory name milk. So what we need to do is two-step process. One of them is identify who's the cows in here, which we can do using the speak function. Well, actually we'll need to add an extra function, which is I wanted to add it in the beginning, but I was like, I won't add it. And the second part is, once we identify who are the cows, we are going to have to cast the pointer back down. So downcast back to a cow so that we can then call the function. And that we have to do this two-step process, because we can't just call it on the parent like that, because it's just like there's no such thing. So even though, for example, spoiler alert, we know that the odd ones are the cows, right? So we have, the odd ones are the cow. So I know for sure that this is a cow. Like, I know this is a cow. But if I try to run this, it tells me that, nope, because you're using it on the pointer. So I still have to cast it first, okay? So that's when downcasting and dynamic casting will come in actually useful in practicality things. So, yes, imagine some weird things. Yeah. So, I guess we'll do that first. We'll do it the way that we know, and then we'll actually do a specific way to identify. So first, because we know ahead of time that imod2 will give us the cows, we're going to take advantage of that. Why not? And then we'll try to actually implement it into the class. Okay? So yeah, we'll just do it like that. This guarantees us that any time that this line of code runs down here, in fact, I'll even do parentheses just to make it pretty, that this technically are all cows. This is guaranteed that these are all cows. However, I still can't get the thing to compile. What I'm going to have to do is do the casting. So I can do the casting in one line of code, do everything, but I'm going to do it first in 2 lines, and then I'll squish it all to 1 line. What I can do is I can make a temporary pointer of cow type. So we're going to call it cow pointer. And then I can go ahead and assign to that cow pointer basically the animal. However, again, you're surprised at how it works, but it shouldn't. I'm going to get the thing saying, well, here, let me get rid of the error so you don't freak out. I'm going to clean this up. I'm going to get the error again, the one, the invalid conversion, okay? Remember that one that we started the day with. And then I don't know why I'm getting the other error. Oh, because I lost the for loop one. So I'm gonna get that error and nothing else other than that error, which I'll solve with the dynamic cast. Because if I try to do it with the static one, I think it won't fix it basically. But here, let me show you that. Okay, so that one's just to give me the exact same error. It doesn't give me the error. Oh god. It doesn't. Great. Now it doesn't. But see, I did like 10 minutes at the beginning of class trying to not make it give me the error, and it was giving me the error then. But now it's like, nah. Oh, no. Yeah, no. So, well, I don't know what to tell you other than it's not giving me the error, but in theory this is really bad. Because if I now get rid of this, I can go ahead and call cow milk on all of these guys. Where's my milk function? Oh, it's private. Okay, that's okay. I can fix that. Oh wow. Yeah, it's a bit of an issue. These are all private. I should have made them public, but I got away with it because of some weird stuff with the V table getting confused. Okay, no worries. So that's bad right there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now we're milking the dog, the pig, and the cow. Okay, so yeah, this is bad, and the fact that it's static cast is letting that happen. Where if I did dynamic cast, then it would segfault. Or doesn't segfault because we're not accessing variables. But if we also added in a variable to the dog, to the cow, like liters, you know, liters, like we could milk 10 liters from the cow. Well, that's excessive. 1 liter from the cow a day. But if we wanted to change that by saying cow PTR liters, you know, plus. Let's say this is actually the number of liters we've milked from a cow or something. Now we get a segmentation problem. Good. So there's 2 things to learn out of this part. First of all, when I tried to do this badly in the beginning, it wouldn't let me compile. But now it did let me compile. So I don't know what to tell you about that other than this is what I'm trying to show you in the beginning, how it's a bad thing to do, but we can fix it. So it's great, you know. I don't know why in the beginning it wasn't letting me compile, but now it's letting me compile. So this is really bad. As you can see, if I switch it back to static cast, this is just a complete another mess what's happening here. Because right now, I am converting all of the pointers to cows. Even though they're not cows, they're dogs and pigs and also here. And not just that, but I am increasing some sort of liter amount in these. And it's not crashing. And the reason why it's not crashing is because here's the thing. Somewhere in memory, each of these objects is located. And only the cow objects have a liter variable. But for the other ones, what happens is this. In main memory, Apple ID signing requested. Somebody's trying to sign into my Apple ID. Let me check if that's... Oh, that is indeed Sam. Teaching class. Oh, okay. I thought... let me give him the access code. Okay. So, okay. Hacked on stream. Yeah, no, literally, like, I was like, okay, I better make sure this is actually a legitimate logging attempt. So, yeah, okay. So, yeah, so he was logging into Apple account. So, yes. Okay, so on memory, we know we already kind of know pointer arithmetic. So I mean, heck, I think it was in your midterm, but we're gonna take that a little bit further now. We know that when we have an array, and that array is a pointer, it's pointing just basically. Oh, I got another one of those. I guess he wants another one. 6. There we go. Okay, so we got an array, and it's pointing basically to spot 0. That's what it is. What is located there essentially? Okay. With classes, it kind of works similarly. When you have a class pointer, it's going to be pointing to the first element in your to your first member in your array. So if you have like int y, int x, foo, and then like int z, PTR is going to be basically the same address as PTR y, and we can prove this by couting it like that. Okay, so if I want to access PTR, x, which is kind of what you did in the assignment 6, is all you really have to do. I mean, yes, you could do this, but really you just have to basically add the space that y takes. And if y is an integer, it takes 4, then you could technically just go ahead and do the address of PTR, or if PTR is an address already a pointer, then it would just be simply PTR plus 4. And that is going to be basically the same thing as this. Okay? I don't know if foo will itself take space in here. That I can't remember off the top of my head. But if it did, it would be at PTR address 8. Like that. If it doesn't take space, then PTR 8 would be z. Okay? Can't really for sure remember if the functions are. I think they don't. But I did see the c here, so we can figure that out. So, and if there's inheritance involved, let's say that you inherit something, more than likely the parent's variables are going to be first, and then the child variables will be right beneath it. So that is why if I have a cow and if I have a dog, there's a string pointer, and it's just a pointer technically, even though it's just a string in there, and I don't put the pointer thing in there. Strings are just it's a fixed size object that's has certain information in it, but the actual text itself that you store in a string is dynamically allocated somewhere else, and that's because you need to have a fixed size of the string. Otherwise, you wouldn't be able to know how big the string is. So in the current way that we did the animal class, that's all we have yet, and so that is going to be I don't know. I think it's 30. We'll check. We'll check how big that is. But that's going to be your string name. And dogs and pigs just have that. But the cow has that. And then right beneath that, it has the leader integer. Okay? And so let's figure out how big actually is. And I'm curious. Let's see how big how big is the string is. And the way we can figure that out is we can see where leaders is stored. So if I go ahead here and say cout, I'll switch it over to the thing. Cow PTRs, leaders, address of that, compared to the address of name. And we're still doing nasty code here, but at least we'll get to see how the shift is there. Inline, so we can see it better. We can see that the shift is 2 values on the second significant digit. This is hexadecimal. Each of those is 16. That means that it is 32 bytes. 32 bytes, not 32 bits, but 32 bytes. Okay. So that's actually what I expected. I think I might have said bits earlier, but I meant bytes. Okay. So that is how big a string object is, regardless of how many characters it actually contains. And that's again because there's a pointer in that string object that is actually pointing to some array of characters that's in the heap. And that can be big or short, it doesn't matter. And that's nice because it allows us to basically have a fixed size of that inside of classes and other things. Okay? So how big is liters? Well, that should be about 4. But the point is this. For the objects here that are not actually cows, that don't have a liter component to it, these are invalid locations, which are just being plus plus. And those could have garbage in it, which if it has garbage 20, now it has garbage 21. Wouldn't uncommenting if fix the issue and milk being yeah, it would. But before I do that, I'm trying to show you why this is actually not crashing and what is really happening, right? So what is really happening here is, yes, this is bad. For the cows, it's okay. It increases actually the value of liters. We can even go ahead and see out what liters has afterwards. So here we can just copy this line of code and then remove the ampersand. So here we can see that liters is all over the place. Like for the actual cows, it actually has a 1 as it should, because we started out at 0. But for the ones that are not cows, like the dog, it has a 50. The pig has the 66 here. Then it has 66 here as well. 66 here as well. That's weird. And then all of a sudden, the last pig has 1042. So these are totally random values. As you can see, this is bad because we're accessing memory we shouldn't. And this actually doesn't crash here, but it could crash in your computer or it could crash in Sally. I don't know. It might not. But either way, you're accessing memory that you shouldn't. But I just want you to understand why it's happening and where that accessing of memory is coming from. It's because of the shifting that is happening, because that's where it expects to find the location of liters, but it's not where it actually is. Now, yes, the solution to all of this, of course, in this specific scenario is just to go ahead and only call all of the cow stuff for actual cows and not other animals. But I just wanted to basically make it a point to show you that, you know, what is actually happening when you're not doing the right thing. Now, here's the thing. Why would it crash? You know, I should probably done that before I did this. Here, I'll comment it out again one more time. Why would it crash when I switch this to dynamic? And the reason for the crash, as you can see it here, is yet again, we're looking at address 0, because what happens is this. When you're casting something that is not a cow into a cow, when you're downcasting something that was animal, but that was really not a cow, which means that there isn't the liters, we actually want that to be a problem. We want it to be an error so that we don't do the weird garbage stuff. And dynamic cast will do that for us because it'll return a null or a 0 when it does the casting and it fails. That is why there's a 0 stored there. And because 0 is such a very, very big different address than what we currently have, that will indeed segmentation fault. So the only part of this that I can't really explain to you is why this actually compiled this time and why it didn't compile like earlier when I was testing it on individual variables, you know, that I'm not sure. But either way, it's a bad thing to do. So finally, we go ahead and fix this so it only gets called on cows and it doesn't get called on anything else. Did I not fix this part? Oh, I see. It's getting called on the dog as well. That's why it's right now problematic. So it's still getting called on the dog. So how do we fix the not getting called on the dog part? Basic logic. I guess there's probably a smarter way of doing this, but we're gonna say it's not equal to 1. Okay. Or 0 actually, because it's on 0. Yeah. So there we go. Okay. So that one almost slipped by actually. We almost milked the dog. Poor dog. But yeah. Now we say wolf, oink, moo, and then we got our milking. And then so the other animals are just speaking, whereas the cow is being milked along with mooing. Okay? So the last thing I want to show with this example is this kind of worked out nicely because we know that all the cows are in even places, right? But here's the thing. Suppose that they're random and we can't use something like this. What we can do is we can go ahead and add a function to the parent class that returns a string or a character that we can then use to figure out what they are. So typically, it doesn't really matter. I mean, you could do like an enum system or an integer for a specific value. It doesn't quite matter. In my case, I'm just going to go ahead and take advantage of the ability for them to speak because they all speak different things. But in this case, it's going to be a valid returning function, which very popularly is called who am I. Okay, and I'm also going to make it virtual. So I'm going to make sure that all of the derived classes define this. You know, and ideally, not ideally, necessarily, you want them all to define it with a different value, okay? And so now, this is going to return who am I. It's going to return actually a string. Well, this is technically a constant array of characters, but that's okay. Like that, okay? And we want to do this for all the functions. Sorry, for all the classes. Where is the typo? Line 57. Oh, I got rid of the for loop, so there's that. Okay. Okay, cool. I don't like this bothering me, so I'm gonna make a quick constructor here. There we go. Okay. I could have made it C++ 11, but whatever. So, yeah. Okay. So now that each of them can identify themselves, I can simply go ahead and put in my if statement, because it's the function itself is available. It's available as a virtual function in the parent class. So I can say if animal farm I, who am I, which will return to us the animal, is equal to moo, then go ahead and run this code. And now this version of the code will work no matter what ordering the animals are at. Okay? Oh. Yeah. It'll work just fine, no matter what the animal is. This is how you normally would do it. So now you have the power of being able to keep a common parent pointer, an array of common pointers, which point to different objects of child objects that are different classes. And then using this who am I function, when it comes time to actually work on one of these objects, you can cast it back to the right animal. So you can downcast it back down using dynamic cast to make sure you don't make any typos. You know, that will be sort of your cover, and then you can work with them. Now the last thing I told you I'd show you is how to do this all in one line. So I'll just replace one of the lines with it. If you want to do this whole thing as a single line, you can just grab all this like this, and let's say we do it on the leaders. You can just do that, you know, for each of the lines. Dynamic cast, cow pointer, animal arrow leaders. So you can do something like this. As you can see, it's the same thing as just creating the pointer. Which, if you have, like in my case, I had pretty much like 1, 2, 3, 4, 5 lines, then I would go ahead and just actually create a temporary pointer like I did. But if you're only doing 1 line of code, then you can do it all in 1 line like that. The dynamic casting, I'm assuming, takes time in the computer to run. So actually, it's worth it making that other pointer. I guess it's actually more efficient and easier to read than having this in thousands of lines of codes, you know. So yeah, that kind of wraps up that discussion. So are there questions on that? Oh, wait a second. So if we switch the dynamic to static array, will it not work perfectly? No, it'll work the same. We can even do that really fast. What matters is that it's an array of pointers, which you can have an array of pointers that's static. You can say animal farm pointers. Animal farm or animal farm pointers cap. I'm gonna have to switch the arrows to dots here, I think. Actually, yeah. No, I don't need to, I think. Expect initializer. Oh, goes there, not there. I'm still thinking of the new thing. So there you go. It works the same. I just did a dynamic array because I wanted to practice that. But yeah, again, you're making an array of pointers. So no, it'll work just the same way, as you can see. Okay. So this concept of calling speak, which is a function that is shared amongst all of them because it's a function of the parent class. This concept of being able to use the word speak, but it's doing different things depending on the object. Now here it's very simple, it's just speaking a different word. But the concept of calling the function speak and it doing different things is a very, very, very powerful concept of computer programming, and it completes our little Triforce symbol of object-oriented design or object-oriented programming. So if you remember back when I first talked about object-oriented programming in like week 1, I think. Yeah, I'm pretty sure it was week 1. We talked about. Well, I never do this Triforce symbol or trifecta or whatever, but now I will. Oh, that does not look equilateral. Neither does that, but we'll just go with that one. Okay. So, you know, this is object-oriented programming or object-oriented design. Two things that mostly mean the same situation. We have the concept of encapsulation. That is the idea of combining data and operations on a, basically putting all your data together and the operations on that data. So data together plus operations on that data, all in a single unit or a single capsule. Okay, so that's encapsulation, very powerful feature, makes life easy, right? We also talked about inheritance. Inheritance is the ability to create new objects from existing objects. So create new classes from existing classes, but basically extending them and adding functionality, but still keeping the main parent class to not have to copy paste code, right? So okay, not old, existing is probably a better word. Again, the main advantage of inheritance is being able to extend upon code without copy pasting, which of course can cause problems and also make it harder to update things. So now, with what I just showed you with the casting stuff, you can go ahead and have the ability to use the same expression to denote different operations. And that is going to be the third corner here, which is called polymorphism. Okay? Polymorphism, if you look at the, I suppose, what is this, Latin or Greek, I don't know, is poly means multiple, like polygon, multiple sides, and morph or morphism is changing shapes. It means to be able to change shapes, to morph into something. So polymorphism means multiple shapes or multiple faces per se. But the definition that we're going to give it here in computer science is the ability to use the same expression to denote different operations. And in the basic sense, that means, like, for example, when we use the word speak. So we have a pointer of a base class called speak. But depending on what, using virtuals, and we achieve this, I suppose you can say this is achieved in many different ways. But right now we're achieving it using virtual functions. It's a combination of virtual functions and also casting, but really with virtuals, we're kind of doing that. Because the mixture of having virtuals plus having a generic class and then having a pointers that are, you know, all these pointers are of the parent class, but they're pointing to different children. So by having a virtual function on the parent class called speak, we can call that class function, and it will call different functions depending on what the object is. If it's a dog, a cow, or a pig. And that ability to have the compiler and the runtime system basically call the right function and do different things depending on what the object is means that we don't care how it works internally. We know that when we say speak, it will call speak on the right thing. Okay? Oh no, you guys will have way more homework. You have to have at least one on template, linked list, and one other thing I can't think of right now. But yeah. Oh, recursion, which we still got to talk about. So yeah. So you will at least have 3 more that I'm legally required per se to give you. And then anything after that is optional. But yes, you have to have at least 3 more. So anyways. Yeah, so coming back to this, that is sort of the important third part of object-oriented design, that you can achieve polymorphism. Now, there are other ways to achieve polymorphism, which is going to be templates and what's the other thing you can do to achieve polymorphism? Well, function overloading in a way, technically. But there's a difference between compile time polymorphism and runtime polymorphism. Compile time polymorphism are things like templates and function overloading and overriding, I suppose. Runtime polymorphism, which I would say is the pure and real version of polymorphism, is really only achieved through casting and virtual functions. Okay, and a lot of people get scared with that term, but it's not rocket science. Okay, so yes, we will talk about templates at some point, probably on Wednesday or maybe even tomorrow, depending on how far we get with the other things I wanted to talk about. But yes, okay. Any questions on polymorphism? And again, we will revisit the term. Yeah, function overloading and templates is the compile time polymorphism, whereas virtual functions is runtime polymorphism, which I personally think is real polymorphism. It's as simple as being able to say A plus B, but A and B could be integers, or they could be strings, which is concatenation. Either way, or doubles, which is still addition in math. You do the both plussing, and it will basically snap them together, you know, or in the concatenation, or in the term of adding, it will add integers or doubles regardless of what they are. Can you explain what it's used for again? It is used to make people's lives easier, because that's the whole purpose of object-oriented design, is to make coding easier and faster and safer, I suppose. And safer by the sense of like less chance of crashing or bugs in it, and easier to update and fix. And so polymorphism allows us to write a function that is shared amongst all of the, and more readable too, yeah. Polymorphism allows, well, there's a whole concept of readability, writability, and reliability, which you'll learn in CS 326. But yeah, so polymorphism allows us to have a function in a parent class that is generic, per se, and generic is an iffy term because that's more a template term, but it's sort of a general function, which then gets defined into different tasks that it can do, but it's still the same function called speak. So we know that the speak function will make the animal speak. We don't know internally how it's implemented. We just know that it will speak. And if it's a dog, it'll woof, and if it's a pig, it'll oink. That's all we know, and that's all we care about. And the power that we can have different things happen, you know, depending on what the object truly is, that is polymorphism. Multiple shapes, right? Polymorph, multiple forms. We don't care how it happens. We just know that if we say speak on whatever animal we have, it's going to pick the right animal's voice and speak that one. And that's a very powerful thing. I know it seems very simple thing, but it's very powerful. And when you see what I'm hoping to be the final project assignment, then you will see how that is very useful. So, yep. Okay. So, going back to the list of things that we want to cover today, that was actually one of the big ones. But the next thing that I want to jump into is assignment 6's last vault. So, this is a little. Let me talk to you about Reinterpret cast. That's the last of the. I guess I had this polymorphism example. Let me talk to you about how Reinterpret cast works. So we talked about static cast. That's the regular one. Dynamic cast, I think now you kind of got a feel for that. It returns null when things are bad. Reinterpret cast, which I like to call YOLO cast because it just does whatever it wants, is basically a cast that does no real. It's only good for pointers. Don't try to do irregular objects. But if you're casting pointers with Reinterpret cast, it's like it'll cast whatever you want. You know, it'll cast it and then it will not check it, and it's just gonna be like, you know, good luck, because I ain't helping, basically, kind of thing. So Reinterpret cast is actually coming from the C days. C days. You know, C++ is pretty much coming off of C, the C programming language, which is kind of like what it's based on. In fact, C++ is, for the most part, backwards compatible with C, which means that if you run C code on C++ compiler, it should compile, minus a couple of little things that don't transfer over, like void pointers and that sort of thing. But I'd say that like 95% of C code would actually work on C++. That's intentional. So one of the things that they sort of kept from that is the ability to have this Reinterpret cast, which is just kind of have a pointer and not care what type it is. Don't do the type checking of the pointer, essentially. And so we can use that to access private variables and classes. And that's how I show it to you in assignment 6's last vault. So if you have a class A, and class A, it has all privates. In fact, I shouldn't have to put this, but I'm going to put it just to make a point that these are for sure private variables, okay? So I got X, and I got Y, and maybe I have also a double G, okay? So you know that you can't access private variables normally, right? Well, here's the thing. Before I even kind of get to that, let me talk about the this pointer, because that'll actually help out a lot. So what is a this pointer, okay? This pointer, like that. This pointer is a pointer that all classes have, okay? At least unless it's a static class, which in case it doesn't, I don't think it'll have one. But if it's not a static class, then they have a pointer which basically points to the first item in the class. So when I was talking earlier about how arrays point to the first element and then classes point to the first member. That location here happens to be also known as the this pointer. And classes actually keep track of that as well. They sometimes have somewhere in the class the location of it. It doesn't have to be, but you can do it if you want. It can be very useful to know where you live, because when you're calling a function, you know, you may want to call it on a specific object's address. And if you want to find out your own address, well, there you go. That's a this pointer. Okay? So if you ever see a piece of code, say we have a public function, sorry, called void foo, and it says this x, that is the exact same thing as this. Huh. No pun intended, I suppose. The this pointer is just the address of the object, and then it's saying of that object this variable. So it's a pointer to the object, essentially. That could be very useful to pass around to other things. I think you saw a little bit of it in operator overloading videos, and if not, you saw it in the tutorial discussion for assignment 6, but also for the, I think for the animal assignment 4 with the pointers. So you probably have seen this in other parts, you know, hopefully, and the book as well. So hopefully this is not the first time you see this. But even if it is, all it is it's a reference to the object, to itself, essentially, which could be very useful to pass around. It's a self-reference, yes, as you said it there. Very good, yeah. And so it also happens to be basically pointing to the first class member. And so if I wanted to access private variables, you know, I could actually do something like this. I could say A is going to be, it doesn't matter if it's a dynamic object or a static object, but I'll just make a static one. And then if I want to figure out where that object is located, you know, I can always go ahead and do something like %A, you know, and this would tell me the address, right, of the object. But I'm also going to go ahead and write this function called foo, which is going to see out the this pointer, just so you can see where that is actually at. And this should actually be the same thing, but let's confirm that. Let's actually call foo here. G++. So as you can see, they are indeed the same address. That's the address of the object that I say A, and also the address of this. And it makes sense because, again, this is a reference to yourself, so it basically has the address. And again, that's a very useful thing to do. Okay, so here's the thing. Let's just cheat ahead for a second and see where the address of X would be. So I could either do something like %X, that would tell me the address. I could also do this X address, % of that. Any of these would work, okay? I'm just gonna pick that one just because we're kind of in the mood to use this. Notice that it's also the same location. Again, that's because think of it like the arrays. Arrays point to the first element. Classes and the this pointer point to the first member variable, okay? So, even though X is private, you know, let's set these to something. So let's go ahead and set these to 10, 20, 30. And I guess we will compile so that it doesn't complain. C++ 11 with that. Okay. So right now, and yes, the addresses do change between runs, but they're still the same 3 addresses, you know, like same, and same. So now, even though this is a private variable, right? If I say cout A, this will complain. It's going to be like, cannot do this because it's an object of a class, right? You know, big errors, big scary errors. But if I cast this to an integer, let's try casting it first the old school way. You know, well, first of all, I gotta cast it. I gotta cast the address of this actually to an integer. So cast that address to an integer, and then dereference it, right? So actually, let's skip to using static cast. So I want to cast this into an integer pointer and then dereference that, because I know that it's actually a pointer that holds x. If I do this though, I'm getting an error saying that this is an invalid cast, because this is a and this is an int. So then you're like, oh, okay, I know how we solved that earlier. We just use dynamic cast, right? Because that's kind of more relaxed and wastes of compile time. But even then, you still get the same error. This is when your YOLO reinterpret cast is going to come to the rescue, which really shouldn't come to the rescue in the first place, because you shouldn't be doing this in the first place. But yeah, okay. So in that case, it'll compile, because reinterpret cast is like, you want it done, it's done. I don't ask questions, I just do it. And bam, I am accessing a private variable because I've casted this. Furthermore, I know that if I add +1 to this address here, so if I go ahead and now that this is an integer pointer, if before I dereference it, I add +1, which means one extra integer ahead, this should give me the next integer, which should be the g. I got a 0. Why did I get a 0? Reinterpret cast that. Is this happening first before the addition? It should. Let's try +2. Still giving me 0. Okay. This shouldn't matter, but I'm going to put extra set of parentheses to be extra safe. Maybe it's confused, so let's just try 4. I got 30 now. So 4 gave me all the way to 30. 3 gets me to some garbage value. 2 should get me to the 20 then. But it's getting me to 0. Probably the ordering is different. But anyways, maybe 5. I don't know where the 20 is stored now, actually. Here, let's cheat and see where that's stored. It is stored at address A as I expected. Wait, no, I didn't expect that. I expected address 4, actually, because I assumed that an integer is only fitting in 4 spots, but somehow it's saying it's taking 8. But either way, if that is the case, then 2 here should give me 20, but it's giving me 0. Oh, I see why. I see. Because I'm trying to interpret it as an integer, but it's a double. So I gotta cast this into a double, actually. So that's why. What did you guys say? Boom, I just like that, right? Nothing, you know, your address. Yeah, indeed, you're right about that. So the +1 goes to the next address. It should go to the next address, but it will increase it not 1 byte in increase, but the size of the pointer. So if the pointer is a size 4, then it should go to size 8. I don't know why here it's increasing it by a jump of 8. Like what is being stored in the address in between them is a good question. But anyways, the reason why I'm getting a 0 there is because the double is sort of not happy that it's being interpreted as a double. So if I go ahead and switch it to 4, that I get to 30 because it's an integer. But if I wanted to make a double here work, I need to do another casting to a double here. So reinterpret, cast, double pointer of this thing. At this point, I've lost track of the parentheses numbers that I need here. Shoot, there's so many parentheses. Let me get rid of them. Reinterpret as enter address of A to that, and then add 2, and then do that casting, and then dereference that. Okay, so I think that should give us a 20. There we go. So double casting. First we cast it to an integer, then we added. Well, I guess we'd have done this with 1 cast and then do +1 in theory. But yeah. So that, the reason why I was saying 0 was because I was trying to interpret floating point notation into an integer, which I guess somehow was a 0 at that time, which is beyond what I understand why. But there we go. That's how we get that. But anyways, that's how you do the other ball, which you can figure that out. The one that I want to show you is the other way that you can just break everything at once. And that is by making a fake class per se. And so we're going to make a class called struct because we want to make it public. And that class struct is going to have basically everything that we currently have in class A. And yes, I'm making it inside of main. There's nothing that forbids me from allocating classes or even functions. You know, nothing stops us from doing this. This is perfectly legal in C++. And then I can go ahead and call bar here. That's perfectly legal. Like, it's a free country. You can do that technically. You don't need to start before the second reinterpret cast. In how I had it before, I did have a star. I think I did. I'm pretty sure I did. I had a star. Not in front of the second. Oh, you mean before the first one? No, because the star is just to dereference the address. I only do that one time. I don't want to do that multiple times. I only want to do it once I have the pointer to the right type in the right location, and then I do the dereferencing. So that's why you saw it only on the first one, on the from left to right. Then you only saw one star, as you should. Okay, but anyways, so I'm gonna head and create a struct which has the same organization as the class that's private. Has the same functions. I don't think you need to have the same functions. You just need to have the same variables. But we'll test it first with the same function, and then we'll test, and then we'll go ahead and do one with just the variables. Okay. So as you can see, I kind of got rid of the body. Doesn't really matter. But bam, I just go ahead and do that like that. You don't actually need to have the same variable names as well, but that makes it easier to keep track of. So if I do something like this, then I can go ahead and create a pointer of the struct that I just made, name it something else other than A. We'll call it fake A. So I can make a struct called fake A pointer, called my fake A, I guess. And so now, this is the cool part. I can take my fake A and assign it the address of the real A. Like that. However, if I try to do this, I'm going to get the invalid conversion error. Function declaration definition is not allowed here. Yes, it is. I don't know why it's complaining about that one. But okay, we'll ignore that. We'll come back to why that is complaining in a second. But for now, just the class I can make for sure. So, anyways, fake A, my fake A. Oh, I see why. Curly bracket. There we go. Okay, so now I just get the one error. Thank you for the semicolon one. Yep. So cannot convert A to main fake A and assignment my fake A. Right? Fair enough. I can try static cast and reinterpret cast, but neither one is going to work. So I'm just going to go ahead and skip to the one that will work, which is reinterpret cast. And here I just go ahead and put my fake A. Fake A, because it's the name of the actual class, pointer, and bam, it will compile. And not only will it compile, but now I have access to all of the variables because the struct is public by default, right? Oh, well, I guess it's not right now, but if I just get rid of these things, now it is. And now I can just basically do whatever I want to change the variable. So I can go ahead and say, see out my fake A's X space my fake A's G space and my fake A's Y line feed. So all those private variables are no longer private. because I have access to all of them, and I can even change them if I want. Let's change one of them. And to prove that it actually changed the real one, let's go ahead and write an accessor function here called void get g, which just counts g. Okay, and so now if I call on the real a, which has a dot get g, you'll see that that actually prints 99. So there you go. Quote unquote hacked. So yeah, no, it's good that you learn it on your own, because that means you probably retain it better. So it's good that you push through that fight together. So yep, you can do that. You can make a Destruct doesn't have to be inside of main, although in the assignment I require you to do it just to show you that you can do it. I guess I thought I could remember being able to do functions inside as well, but I guess that one is not happy about. Maybe if I put my own scoping rules, like if I put my own scope, it'll let me do that with the function. I seem to recall doing that, but I mean, this might be too much Python in my life to get them mixed up. It's telling me it's not allowed to put a function, so maybe C++ does not allow you to do the function in there, but it definitely allows you to do the structs and namespaces as well. So yeah, ignore the function thing I said. Python is too much in my brain. So yep, that's that. So that is how I want you to do the last vault, but you can't use this method for the other vault. For the other vaults, you have to do the pointer arithmetic that I showed you before I showed you this method. So the one that I did right before this one, I was doing the +1, +2, +3, +4, which may vary slightly than what I showed you depending on Sally. And the last thing I guess I want to show you is that I didn't want to put it in because I wasn't 90%, I was like 99% sure if I remember correctly, but it doesn't matter. The functions don't matter. What matters is the order of the variables. This order has to match what is in the original class. That way, the arithmetic that's happening here matches. So, yep. So in summary, today we covered almost all the things that I wanted to cover. We didn't cover yet virtual destructors and virtual inheritance. We'll go ahead and touch upon those next time, and then we shall move on into talking about templates. I think that's what's next. So virtuals is a very, very cool, powerful thing. Polymorphism, as we saw, is achieved through that, but we also see how compile-time polymorphism is done with templates. But I will go ahead and let you guys get assignment done for now, and we shall reconvene tomorrow to continue talking about this. I'm kind of glad beginning we kind of started out iffy. I'm still not sure why I couldn't get that to compile when now it compiled, but yeah. Yep. Any other questions or anything of the sort, especially with the assignments? As you saw, I did move that assignment because I didn't realize I made it due the same day, the day after I would talk about things. But yes, and yes, you will get more assignments, at least 3 more, possibly more. We'll see. I did warn you guys on day 1 that this is a tough class because you do have to basically be coding every single day. Can you please tell us why we need to change the value of KV6 to 0 for assignment 6? Just to prove that you can, just kind of did here that you hacked it. So it's just part of the fun, to show that not only can you read stuff, but you can also modify it. So that's why I wanted you to change the 0 on that one. Sometimes when I see out the Reinterpret cast, it will output a random huge number. How would I fix that? That is a sign that you're not pointing to the right value, because you saw me do the same thing here. When I was not getting the right addresses correct or the right data type correct, you saw that I was getting like random values like this or this. That is because I'm not pointing to the right location in memory, because your pointer arithmetic was off, or you're not interpreting that value with the right type. So like if you're trying to interpret as an integer instead of a double, or in the case of the assignment as the num class type that I made. So yeah, that would be the reason why you get that kind of error. So go back and look at the pointer arithmetic. Turn on the debug mode to see it and kind of get a hint of to where things should be. Anything else? I'm gonna go ahead and erase these two things from here, since we will no, I'll do it after the lecture ends because I want to copy and paste this for tomorrow. So, yeah. Additional questions, you can just let me know on the Discord, and I should be awake for a little bit longer. It's been a long day. Will we have lectures next week as well? You will have lectures Monday, Tuesday, Wednesday, Thursday this week, and then next week you will have a lecture on Monday, Tuesday, and Wednesday, and then there will be the exam on Thursday, and then that will be the end of the class. Although I will probably make the last assignment due after the exam, like on Friday or Saturday. That way you have extra time to do it. Because yes, you do have quite a bit of work to do left. We have at least 3 assignments, and then potentially the final project, which I'm still split upon which of the 2 I want to give you. Of the ones that I could give you the same that I gave last spring, but I also want to try to give you a different one because it's no fun doing the same thing over. Plus, there might be solutions on the internet, so yeah, can't let you cheat. Why not give us both? That's a lot of work. That would be too much work, actually. The one that I want to give you, I think, is the assignment I gave my 302 class as a final project, but a watered down version of that. It doesn't require the 302 aspects of it. That's one scenario. Other scenario would be to do the Inception assignment, and then other scenario actually could be the Battle Royale assignment, but that I think is better to do the CSVO. So I'll figure it out. I'll just basically put them on the wall and throw a dart and see which one it goes into. So, yep. I'll try to make the other remainder assignments publicly available before we talk about the content, if you want to try to get ahead over the weekend, this weekend. But otherwise, be ready to be basically coding every day for the rest of the 2 weeks that we have left. It's just the fact of life. Ask people who've taken it in the regular semester. They get about 16 assignments for the full class. So yeah. Cool. All right then. I shall see you guys tomorrow then at 5 p.m. Yeah. So thanks for watching and have a good day.